I should get a perm, right? Except for I don't have hair right now, so I need to let it grow. Come back next year. Permutations, all what I'm going to cover first, or what I need you to understand for permutations, for you to be able to use permutations, the first part we're going to just focus on where all objects are distinguishable, they're unique. Okay. NPR is the notation used to represent the number of permutations or combinations that can be made from a set of n different objects, where only R number of objects are being used in the arrangement. Okay? And this is something that is always true. R has to be between 0, but it has to be less than the groups themselves. Okay? This implies no repetition. Go ahead. Yeah, go ahead. Make sure you understand that permutation can only be used when there is no repetition allowed. So when it comes to people, or you're drawing cards or anything like that, you have a limited supply. So let's make another note here. Limited supply. So you're thinking cards, marbles, people, etc. Okay. Oh, letters in a word. Okay. Should I say that? Hold on. Let me just comma, letters in a word, that's definitely permutations because you only have the letters that are in that word. That's all you have to pick from. Okay. So I'll give you some examples there. This is the formula NPR. Okay. So to figure out what NPR is, you would take N, put a factorial to it, and then divide it by N minus R factorial. Okay, so there's the N, there's the R. So this is the formula for it. I would say have this on your study sheet. Okay, make sure you have this on your study sheet because I often ask you to evaluate it. Okay, and so I will say that one more time. N is equal to the number of options you have. Like, what are the total number of options you have available? And R would be the number of slots to be filled. Okay. Think of it that way. So we're going to word problems. That's where I really want to go, but I will show you a couple of just basic calculations. If I ask you 5p2, it's like evaluate that, use this formula right here. Okay, so this is n and that is r. Sorry, it's very small, but I hope you can see that. So there'd be 5 factorial divided by 5 minus 2 factorial, which ends up being 5 factorial over 3 factorial. This is on page 18. And if I asked you to simplify it, show your work, you take this, which one is the greater one? 5, right? You know that already. So 5 times 4 times 3 factorial divided by 3 factorial, cancel it. This is just beautiful. It's 20, right? It's 20. So I'm just going to make a note here. If I ever ask you to simplify, I want like the steps you took to come up with the answer. I know you can plug it into your calculator, right? I know it, and you can do it to check it. So let's do that right now. Grab your calculator, and you basically type it in the way you see it. Type in 5, and I'm going to go alpha window. not the other one, right? Alpha window, and go down to where it says NPR, right there. Hit enter. So the 5 is already inserted, and then just hit a 2 and enter. And there it is. It's 20. You should be getting 20. We're good with that? And now I'm just going to copy paste. Like I don't like to. So there we go. I'll do one more. I'll do this one here. This would be 100 factorial over 100 minus 2 factorial. This would be 100 factorial over 98 factorial. I don't know if this lets you do it, so I'm gonna try it here. 100 and then 98, like this. Oh, sorry guys. 102, right? Not 98, my bad. Yeah, it does. Okay. But if I ask you to evaluate it, you just go 100, 99, 98, slap a factorial over, and then go 98 down here, cancel it out. That's 9900. Okay. So you should be able to get that as well. But here's something even maybe cooler. I don't know if you would agree with me on this. I'm going to get rid of, no, I'm not going to get rid of it just yet. But when would you be using this permutation notation? I asked you on the AC to give me 2 methods. Think of it this way. If it says 5p2, really what it is saying, using the fundamental counting principle, you start with 5, and then the next option would be 4. So this 2 tells me that there are 2 slots to be filled in, and you start with whatever your total is. So in this case, it's 5 times 4, that's 20. This is using the fundamental counting principle. This is using permutation. You arrive with the same answer. Okay. Let's try this one. If you were given this within a context, you should be like, okay, there's 2 slots to be filled, and I start with 100, because remember, permutation only works when repetition is not allowed. Okay, so that would be it. You would start with 100 and then with 99, and there you have your 9900. This is the fundamental counting principle. Okay, I will use a highlighter or something to just show that. So 5p5, what does that mean? How many total options do I have? 1, 2, 3, 4, 5, right? Sorry, this is the slots. That's what I meant to say. These are the number of slots, 5, and you have 5 options. So this is 5, 4, 3, 2, 1. It's actually 5 factorial if you think about it. And that is 120. Yeah, thank you. I'm trying to memorize. I'll actually tell you on your study sheet, write down some of them, because it's a lot faster if you know your basic factorials. Okay. So I'll leave it at that. Okay. It's just 6, yeah. It's just 1 slot to be filled, and how many options do you have? 6. It's just 6. Yeah. Yeah. I'm going to give you some shortcuts. Is it coming up? It's coming up. Maybe even Monday for that. Okay, let's use permutation to solve the following questions. Okay. An artist wishes to display her 8 paintings, but is told that she only has to pick 5 paintings since space is limited. So it's basically saying, hey, you've got 8 paintings, you can only pick 5 at a time to display. Right? How many arrangements can the artist make? And I'll just make a note here. I want you to start thinking of that. No repetition. In other words, limited supply. Right? You only have those paintings. So as soon as you take one, you're left with 7, and then you take another one, you're left with 6. So that's important to note here. So in this case, you would say, using the fundamental counting principle, you would say, okay, you've got 5 paintings that you can display. And so at the beginning, you can pick 8, and then you can pick 7, 6, 5, and 4. That amounts to 6,720 arrangements. Okay. On the other hand, this is the second method, using permutation. So basically what you would say is, well, there's 8 possible options, and how many slots do you have to fill? 5. Okay. That would be 8 factorial over 3 factorial, right? Because 8 minus 5 is 3. And I'm not going to simplify it here. Technically, you can just type it in because I'm not asking you to actually simplify. You could actually just type this in and voila, right? Let's do it. Sure. I can still teach?
Oh, yeah.
Okay.
Time we're not here.
We might do electrical stuff later.
3 minutes.
All right. As long as the power doesn't go off, we're good.
Oh, no, it won't go.
Okay, so for this, we just type in, I'm going to copy that one over there. Let me clear this. 8P5, and there you go, 6720. You need the key? Yeah. Next question. There are 11 candidates that are running for 3 positions. How many possible outcomes could there be? Okay. So again, you would just, using the fundamental counting principle, this could be the president, vice president, treasurer. You go 11, 10, 9, right, essentially. And that would be 990 outcomes. This is fundamental counting principle, nothing wrong with it. Or you could do 11, pick 3. That's another way of reading permutations. 11, pick 3. Okay, so that'll be, I'm just going to come up with a 990. That's all good. Outcomes or arrangements. This is called, we're using permutations here. But you should see the connection, right? If I have 3 slots to fill, I start with 11. It's 11 times 10 times 9, right? That's another way of looking at it. All right. Let's keep going. So we've done this kind of stuff already. Now we're just using permutation notation to do the same thing. Okay.
Thank you.
You're welcome. Everything good?
Yeah.
Perfect. Can I just, I'm going to draw your attention to the grouping here. Highlight that one. Permutations involving grouping. I will ask you to write it even bigger. Grouping. How many ways can the letters in the word grouping be arranged? That's another good question. An artist wishes to display her 8 paintings at an art gallery. That should ring a bell. It's from the previous page. Okay? How many ways can she arrange the paintings? 8 paintings at a gallery. we're assuming that there's no restriction in the grouping, okay? Do you notice that? We're not saying from the 8 you have to pick 5, nothing like that. So it's just basically 8, pick 8. That's basically what you're saying. And what's 8, pick 8? Grab our calculators. So I'm just going to copy paste the previous line. It's 40,320. Okay. I will make a note. We are not told to only pick 5 or less than 8, right? So that's important here. We're assuming we can just arrange all 8 of them, and it's 40,320 ways. Let me use my iPad to illustrate this here. I hope this is going to help you a little bit, especially when we do the grouping. So consider 8 different paintings, 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 paintings here, right? So you have to think, right? This is one arrangement, and then you can copy this. There's no clone. Okay, copy. We'll paste it here. Okay. So this is one arrangement, and as soon as I switch, if I switch these two, that's considered a separate arrangement. And you keep doing that. So you can like move through it, right? And move them around, and every time you just move the order of the paintings, it's considered a different arrangement for us. Okay. Because they're unique. It makes a difference. So that's what's happening here, and that's why you have 40,320 ways to arrange them. So again, 8 pick 8, that means if you were to use the fundamental counting principle, 2, 4, 6, 8. I have 8 slots, and you go 8 times 7 times 6 times 5 times 4. Right? So it's the same. You would get 40,320 either way. Okay. So just use this as a tool or stay with this, whichever one floats your boat. It doesn't really matter to me. Okay. B, if the artist wishes to keep her 3 favorite paintings together, that should indicate to you that this is grouping. You should read that. Any problem I give you is like, oh, we're keeping them together. Okay, got it. They kind of stay together. Okay. How many arrangements are possible now? I'm going to use my iPad in a little bit, but I have a method here. This is what we're going to do. We still have 8 paintings, so make 8 lines. 1, 2, 3, 4, 5, 6, 7, 8. Don't use up too much space. Okay? So if we assume the 3 paintings are right here, okay, this is your group, and they stay together. Okay, they stay together. We can move them, but they always have to stay next to each other. Okay, that's the assumption we make. In this case, watch this. This is considered one slot. So you've got 1, 2, 3, 4, 5, 6. 6 slots in this case. Okay, so we would say for sure 6 factorial ways. And I'll show you a formula in a bit where you can always do the grouping right if you follow my formula. However, if you look at my, I'm going to get rid of this here. Can I just do undo? There. So 2, 4, 6, 8. I still have 8 paintings. Let's assume these are the 3 paintings that I want to keep together. I'm going to group it. So now I can, when I move them together. So this is one arrangement. Then I can move that one over. That's another arrangement. and move that over, another arrangement. So they're always staying together. So we consider this as like one block. It's almost like there's only 6 ways to move things around because we're grouping these ones, okay? So that is partly true, but at the same time, you can actually take these ones apart and move them within that little group, right? Would you agree with me? You can also move things within that little group as long as these 3 stay together. And that's where the 3 factorial is going to come in that I'm going to put in front of that, okay? So what I do is there are 6 slots, okay? That's where that 6 factorial comes in. But you multiply the permutations that happen with this group, you will multiply that by 3 factorial on top of it. And put the 3 factorial inside this little circle. And I'm going to use a highlighter there for this. This 3, that group goes in here. Okay? And the 6 slots, right? The 6 slots are counted because this is one slot. 1, 2, 3, 4, 5, 6. Okay? So when you make a group, make a circle on it and pretend like this is one line. And then count it. 1, 2, 3, 4, 5, 6. Boom, that goes there. But then whatever the size of the group is, you also factorial that one. You go 3 factorial. If this had been a group of 5, it would have been 5 factorial, and so forth. Okay? Is your head spinning? Maybe. Let's figure out what this is. Grab your calculator. It's good practice to follow along here. I'm going to go 3 alpha window. Get that exclamation mark there. 3. And I think the calculator is okay to just go 6 without times. And copy that factorial one more time. That's 4,320 ways that you could arrange it now with that restriction of the 3 paintings being together. Okay. You want another arrow? I don't know. So the small group, this is the large group, the large setting from a bird's eye view. This is within the little bubble. You got to multiply them together because you're creating 3 factorial more ways if you can move stuff within. Let's do that one more here. The artist looks at the paintings again. She has a group of 3 that need to stay together and another group of 4 that needs to stay together. How many arrangements are possible? Follow me again. 1, 2, 3, 4, 5, 6, 7, 8. There's still 8 paintings, okay, guys? Circle your 3. This is group 1. And then circle any other 4. It doesn't matter to me. I'm just going to take the ones right here for now. This is group 2. Let's look at the bird's eye, like the big picture. How many slots are there? 1, 2, 3, right? There are 3 slots, so we go 3 factorial. Can I do this? I'm going to go green. That's that one. And then to satisfy, because now you can also move within this group, within it. So you're going to go 3 factorial for this first one. I'm going to call this G1, group 1. And the second group has 4, right? So let's put the 3 factorial in there. And there's 4. We can move these 4 as well. So that's 4 factorial. It's group 2. And I will call this 3 slots out here. So that's the last one there. Okay. I will still use pink for the first one here. That's this one. And let's do orange. So in closing, you always have to consider the big picture. After making the groups, how many slots do you have on the outside? Then you multiply that answer yet by the number of people within each small group. Hold on, there's one here. This is the formula that I've used, guys. This is for grouping. I would say highlight this and add it to your study sheet. This is what I essentially is going to help. Every time you apply this formula, you end up with this. So watch this. What you need to do if there's grouping, you take the objects in group 1, slap a factorial on it. Multiply it by the object in the second group. If there's a second group, slap a factorial on it. Times. What does ... mean? There could be more groups. Usually not. Usually there's 1 or 2. That's maximum. But then you multiply that by this bracket here factorial. That's the green one here. This is the green one. You take your total, you subtract the number of people in group 1, you subtract the people in group 2, and then you add the number of groups. So hold on. I want you to try for homework. I want you to try 22 to 24. Make sure you try some equations. Make sure you catch up with your notes. And I'll see you again on Monday. Have a good weekend, guys.